Greetings and welcome to the Pencrest High School AP Physics C video series. This is video 4B, center of mass for solid objects. Now, solid object can be thought of as a collection of particles, but there's so many of them that the summation sigma m x divided by sigma m can be considered prohibitive. So the summation becomes an integral in which some infinitesimally small mass element, dm, is located at some position, and we integrate over the entire volume. We don't need to go this far because the objects we deal with will be what's called uniform and homogeneous. That means that they will have consistent mass density throughout their volume, and their shapes will be regular. Regular shapes are geometric shapes you're familiar with, squares and rectangles and cubes and circles and spheres and so on. Shapes that it's easy to find the middle of. Now, the consequence of using uniform and homogeneous objects is that the location of the center of mass will always be in the geometric center of the shape, whether it's a one-dimensional shape like a stick or a thin rod, a two-dimensional shape like a rectangular plate or a piece of paper, or three dimensions like a regular rectangular cube or sphere that you're familiar with. These shapes typically have axes or planes of symmetry, and the center of mass of a uniform and homogeneous object will always lie on an axis or a plane of symmetry. It's not necessary that the center of mass actually be located inside the object itself. If we think of a shape like a hoop, the center of mass of the hula hoop is in the center of the hoop. There's no actual matter there at all. But if we were going to treat this object as a particle, that's where the mass would be located, right there in the center. So we can conceivably have one, two, or three-dimensional solid objects. A one-dimensional object could be a long, thin rod like we see here. Anytime we have a uniform and homogeneous rod like this, the center of mass is always located at the middle of the rod at a distance L over 2 from either end. A two-dimensional object would be shown as a geometrical shape, a regular shape like a rectangle or a circle. The geometric center of the object is where the center of mass is located. It should be relatively easy, given the dimensions of the object, where that object center of mass is located. Triangles aren't quite as easy. There's a couple of easy methods to determine where the center of mass is. If we have an isosceles triangle like this one, the center of mass is along that axis of symmetry that you see there, the vertical one in this case. And it's 1/3 of the height up from the base along that axis of symmetry. Any other triangle, you can actually connect each vertex of the triangle to the midpoint of the opposite side, like we see here, and here, and here. And where these lines converge, where they intersect, in the middle there is the center of mass of this triangle. Now, if we have a three-dimensional, a realistic object, the center of mass is at the geometric center of the shape. We will use shapes that are easy to locate the center of, so cubes and rectangular prisms and cylinders and things like that, where it's, again, very easy to locate the geometric center. Now, if we have what's called a composite object, it can get a little more complicated. Your daily will consist of a composite object that's shown below. The dimensions here, A, B, C, D, E, are all given. And what we need to do is consider that all three of these two-dimensional objects are made out of the same material. They have the same thickness, which is the dimension into or out of the screen. In order to determine the mass of each object, we would need the mass density in kilograms per cubic meter and the volume of each piece. The volume, of course, is a three-dimensional measurement, length times width times thickness. Since they're made of the same material and they all have the same thickness, what's going to be the determining factor for the location of the center of mass is the area of each of these separate pieces. We have a circular piece here, number one, and we have a rectangular piece and a triangular piece. So we're going to look at it this way. We know that the location of the center of mass, I'm leaving out object 3, the triangle, just for the sake of fitting it on the screen. We know that the center of mass, x coordinate of the center of mass would be m1 times x1 plus m2 times x2 over the total mass m1 plus m2. If we consider that each piece's mass is its density times its volume, and that the volume is the area that we are looking at times the thickness or the dimension into the screen, we get that each mass is density times area times thickness, and then mass times x1 plus the density, area, thickness of object 2 times x2, and then again over the total mass. What we find is that the density and thickness terms appear on each of the three objects, so they will go away. And what were the mass terms in the numerator and the denominator become area terms. So we have A1 x1 plus A2 x2. I'm leaving out A3 x3 over A1 plus A2 plus A3. So the mass terms become area terms. We then would treat each of the objects, the circle, the rectangle, and the triangle, as a discrete particle. So this represents the circle, this represents the rectangle, this represents the triangle, and we place their masses at their individual centers of mass. So this is the center of mass of the circle and of the rectangle and of the triangle. We replace the mass in the formula with the area of that piece. So A1 would be the area of the circle, A2 would be the area of the rectangle, and so on. And then we execute the formula as we normally would. If by some chance each piece were made of a different material, we would need more data, like the density of each material, and we would need to actually calculate the mass of each piece using the area and the thickness. Now, the same rules would apply if we had a three-dimensional composite object. In a case like that, we would need to make a note of where the origin is located. It may seem obvious to say so, but it's where all of the axes meet. Wherever the label for the axis appears in the image, that indicates the positive direction for that particular axis. This may end up different from what your traditional sense of X, Y, and Z axes are. Right and up and towards you are sign conventions. They are not hard and fast rules. You have a problem in the weekly that looks like this. This composite object, we're going to look at the image and we're going to look at where the X and Y and Z axes are. So looking at the image, the X axis is here, the Y axis is here, and the Z axis is here. So the origin is on this bottom left corner. And then where the axes labels are located indicates that this direction is the positive X direction, kind of to the left and down. The positive Y direction is this way to the right and down, and the positive Z is sort of to the left and up here. So when we solve for the individual components of the locations of the center of mass and so on, the iron block and the aluminum block, we would need to indicate those X, Y, and Z coordinates with the proper sign according to the directions that are established by the axes in the image. Okay, so make a note of that and be careful. Okay, so next we will get into the motion of the center of mass. So